idea again was, so this is just a completely new topic.
Can we put it on a new page, or does that make it harder?
Yeah. There we go. New page. Yeah. Okay, and so the goal was to prove the goal, right, is to prove that that this thing for G a finite group, for G a subgroup of Sn, that and K is x1 to xn. Let's say, so this actually, let's do K field of characteristic 0. Characteristic 0. That this thing here, G is finitely generated. Okay, as a ring. And so this is the ring of invariance here. Okay, to set this up, I need to say a little bit about graded rings. Okay, so let me say a little bit about and so the main point here is that the proof of this goes through the Hilbert basis theorem. Okay, and this is essentially that this ring here, K of x1 through xn, is Noetherian. And that says that ideals have a finite basis, right? That was the big deal back in the day, right? Some say is that if you have a ring R that's Noetherian, then if you join a single indeterminate, that's also Noetherian. That's another way that people say it. But the big application is to polynomial rings in several variables and showing that it's Noetherian. Okay, so so I need to say a little bit about graded rings before doing the proof. Okay, so what's a graded ring? So definition. A graded ring S, well, is a ring with a direct sum decomposition. Okay, so d greater than or equal to 0 of SD, which is such that, so this decomposition here is as abelian groups. Okay, so maybe I'll make some modifications to this in a second, such that SDSE is a subset of SDE. Okay, so that's what a graded ring is. And so sometimes, so here, we can modify this a little bit. So you can have a graded R algebra. Well, is an R algebra where the decomposition of SD is a direct sum of R modules. Okay, So in particular, these could be if R is a field, then these are vector spaces. Okay, so so there's a terminology. So the homogeneous elements these are the disjoint union of the SDs for D greater than or equal to 0. And an element F in SD is called homogeneous of degree D. Of degree. Okay, so what are examples of these graded rings? So the big examples are, okay, is S looks like we could do C of x0, x1, xd. Okay, and here SD, well, this is C x0, x1. Oh, sorry, this should be xn here. Xn or D. So these are homogeneous polynomials. Polynomials of degree D. Okay, and so let me say what this is. So f of x0 through xn is homogeneous of degree D if and only if we have this expression. Okay, so that's what a homogeneous polynomial of degree D is. So let's kind of give some sub-examples. So if I did C of x0, x1, 2 here. So this would be generated by, this is C of x0 squared plus C of x0, x1 plus C of x1 squared. So these are the homogeneous polynomial. There's 3 of them, and any homogeneous polynomial of degree 2 in 2 variables is a combination of these 2 things, of those 3 things, right? So yeah, so they're just combinations of monomials of degree D, right? In general, xn of D is generated by x to the alpha, where alpha is D. So here this is, x0 to the alpha 0, x1 to the alpha 1, xd to the alpha d, or xn to the alpha n. And this is, of course, this is alpha 1, alpha 0 plus alpha 1 plus alpha n. Okay, so this is a good example. So how do we get more examples? So so there's a thing called a homogeneous ideal. Okay, so a homogeneous ideal definition. Okay, so let S be a graded ring. The homogeneous ideal is an ideal I in S generated by homogeneous elements. elements. Okay, and so let me just say a little bit about this. Let's just do one example. Okay, so we could do, say, so we could do C, so we could do S is equal to, I don't know, F of x0, x1, x2, x3. And then we could take I to be the ideal generated by x0 cubed, x0 squared, x1. Let's just do ones of degree 2, huh? Oh, let's see. Let's do this. X0 cubed. Let's see. Do we want to do? Yeah, let's just do this. X0, x1, x0 squared, x2, x0 squared, x3. I don't know. So x0. So let me put dot dot dot. So this is. So this is, I'm doing all monomials of degree 3. Okay, so this is something that you could consider, right? This is a homogeneous ideal. So what's the point of this? Oh, let's see. We want to do this one. Okay, so this is one, or here's one example. You could do J. You could do. Let's just do something even simpler. This thing. X1 cubed, x2 cubed, x3 cubed. Okay, so that's a simple one. Okay, one reason that we care about homogeneous ideals is that the zero sets of them are well defined in projective space. Okay, so just kind of like an aside.
In a graded ring, are all elements homogeneous of some degree?
No, not there are always sums of elements of yeah. So not all elements are homogeneous. That's a good question. So so like here you could take, you know, x0 squared plus x1, right? This is homogeneous of degree 2, and this is homogeneous of degree 1, right? But this is a valid element. This is an element of S for this particular S, right? So there are sums of homogeneous elements, but they're not all necessarily homogeneous. Okay, but the ideals, there's elements in here that are not homogeneous, but they're sums of things that are homogeneous, right? So the point is that these ideals will also have direct sum decompositions. But one of the big points is that if you look at like projective space, right? So this is, as we recall from Z0, Zn, right? These were tuples like this, where not all Zj are equal to 0, right? And then we had this thing that these things were equal to lambda Z0 Zn, lambda Zn. Okay, and so the upshot is that for f of x0 to xn homogeneous, right? The subset v plus of f here. Let's put C here. So this is the set of z0, zn, such that f of z0, zn is equal to 0. This is a well-defined is well defined. So when you take homogeneous elements, right, then you can plug in, you can look at their solutions, the zero sets of them in projective space, right? And then this gives you kind of compact versions of algebraic varieties. So in some way, so this tells us that like graded rings. So okay, so the point is the big point. Okay, projective varieties so this is things cut out by homogeneous polynomials in projective space. These things are, this is the geometry side of things. This has to do with graded rings and graded in homogeneous ideals. In the same way that, affine varieties have to do with rings, projective varieties have to do with graded rings. Okay. And so there's a whole geometry to graded rings as well. Okay, and all right. Okay, so now I can start to move towards the application. Okay, so now the invariant theory, and this is just more of a direct algebraic application. It's not so geometric, or at least I don't understand the geometric meaning of this, but it's a cool proof. Okay, so here's what we're going to do. We're going to let A be this ring here, and we're going to have the characteristic here of this field be 0. We're going to let G be a subgroup of Sn. So I think before I said that I wanted this to be transitive. I don't know what I was thinking. I guess I'm doing a project with a lot of transitive groups. This doesn't need to be transitive. Okay, and then we're going to let AG be the ring of invariance. Okay, and so the theorem is that this AG is finitely generated. So there's finitely many polynomials which are invariant under G, such that every other polynomial is a polynomial combination of those. Just like the elementary symmetric polynomials are for Sn, there's a general version of this. Okay, so there's kind of some important facts that we'll need. Okay, there's 2 important facts. The first important fact is that AG is a graded ring. Okay, so AG is a direct sum from I is equal to 0 of these AGIs. Okay, the second important fact that we're going to use is that there is a map. So the map here, phi, from A to AG, given by this formula here, phi f, this is going to be the sum. So we're going to do 1. It's going to be the average over the group here. So what I can do is I can take a polynomial that isn't necessarily invariant, and I can create a polynomial that is invariant by doing this. Okay, so this thing is a map of AG modules. Okay, so in particular, so this means if F looks like the sum of, let's say GI Fi, where Fi is an AG, then what we do is we do this. If we do phi of f of this, well, maybe I should have written the f's before, but this will be the sum of gi's of phi of gi's fi's. Okay, so maybe I should have written. Usually we write modules like the left multiplication in front. So it's supposed to be like an AG linear map. Okay. All right. This map is AG linear. All right. We're just going to assume that. Okay. So let me go give you the proof of finite generation now. Okay. So using these two things, I am going to prove that. So using these facts. These facts and the Hilbert basis theorem so we will prove AG is finitely generated. Okay, so here's the proof. Okay, so we're going to let I in AG, so let I in AG be the homogeneous ideal generated by invariance, homogeneous invariant polynomials of strictly positive degree. Of strictly positive degree. Okay. Now I'm going to extend this ideal to A, to all of A. So since A, this is again the polynomial ring, is finitely generated, or sorry, is Noetherian. So Noetherian again means that all the ideals are finitely generated. We have that IA. So this is an ideal generated by F1 through Fs. Okay, where Fi, these are elements of I. So these are homogeneous invariant polynomials. Okay, so these are so I guess, do I know that they're homogeneous? I know that they're in here, but I guess I don't necessarily know that they're homogeneous. Okay, so but I think, do I need to suppose that they're homogeneous? I don't know. We'll find out. Okay. So the claim is the claim here is that that AG looks like and then what do? We had a field here. So this thing is K F, that these things generate Fs. So the generators of this ideal are the generators of this. Okay. And let me just make a note here. And then we'll deal with that if we need them to be homogeneous. Okay. So okay, so this is what we have. So what we're going to do is we're just going to define A prime to be this ring, and then we're going to show that that this ring and F of S are the same. These two rings are the same. Okay, so we want to show that A prime and AG are the same. So clearly, A prime is a subset of AG. Okay. So conversely, we claim that if f is in if f is in AG is homogeneous, then f is an element of A prime. All right, so this is what we'll claim, and the proof will go by induction on degree. The proof goes by induction on the degree of f. All right. Okay, so we need to show that this f is in this ring. So we're just supposing that it's homogeneous and invariant, and we need to show that it's in this ring, and that these f's here that in the setup, they're the generators of this ideal here. Okay, and so so the base case is easy. If the degree of if this thing is 0, then f is a constant, right? Then f is an element of K, and we're done. And we are done, meaning that that f is an element of A prime. Okay, and so now we'll do the inductive step. Okay, so we'll suppose that that homogeneous polynomials, right, will be of degree will be of so homogeneous polynomials which are invariant and their degree less than the degree of f, right, that those are going to be contained in A prime. Okay, so if the degree of f is greater than 0, right, then f is an element of IA. Okay, and right, f is equal to I is equal to 1 up to s of GI fi. Okay, so I guess we do. So now this is where this hypothesis comes in here. So I guess we do need these to be homogeneous here. Okay, so so we need these, the FIs, to be homogeneous. So we need to think a little bit about that, but let's just suppose that's the case.
Homogeneous of the same degree, or just
no, any degree. Homogeneous of some degree, right? So they're not just going to be combinations. And I think the idea is that I is generated by all homogeneous elements. So you can take a subset of the generators of I to get the generators for IA, right? So some subset of the generators will be there. But maybe we need to do some sort of ascending chain condition thing to make this rigorous. Okay. So you just, so I guess that's what you do, right? Is that you just keep adding homogeneous elements, right, until you get the full ideal. And you know that it's going to terminate because of the ascending chain condition. All right. So so the other claim that you have to think about is that so here we're using that FI are homogeneous. Okay. And then here's the point, is the big point here is that these things are forced to be homogeneous of degree, and then you have to match them, deg f minus deg fi, because each term here, because of the direct sum thing, each one of these has to have the same degree. Each one of these terms has to have the same degree as f. So each one of these have to have the same degree as f. Okay, all terms, so all of them have to be homogeneous. Okay, and notice that this degree, so now the inductive hypothesis kicks in here. So this thing is less than the degree of f. So inductive hypothesis. Kicks in. Okay, and let's look at what happens. So here's the trick. So now I'm going to use, so I've kind of set up everything. I use this like graded structure, the graded ring structure. I haven't used that involution or that map yet. And so what we're going to do is we're just going to do phi of f to everything. So we do phi of f. And so this is a map of AG modules. So that's what I was saying before. So we get phi of GI, FI. Okay. This thing here, this is equal to f. This part here is by invariance. By invariance of f. So f is, f is an element of AG. It's a homogeneous element of AG. This thing here, okay, so by inductive hypothesis, this is now an invariant element. This is an element of AG, and it is of degree less than the degree of f. So that's the inductive hypothesis, and this implies that phi of GI is an element of A prime, right? And then this part here, these are already in A prime. These are elements of A prime, right? And so all of that together proves that f is an element of A prime, which proves that, AG is a subset of A prime. Okay, so then we show, so, and that proves that AG is finitely generated. So AG is equal to A prime, and hence is finitely generated. Okay, so that's the proof of finite generation of the ring and invariance. The crappy part about it is that it doesn't give you the basis, right? It doesn't give you the generators. It just shows that there exists a set of generators, and this is what people were really upset about in the late 1800s. They were just like, this is a non-constructive proof. There was like a whole like constructive, non-constructive beef going on in the late 1800s, and people were kind of heated up about it. And this is one of the things that was, Hilbert was starting to do crazy things with it, and yeah, so yeah, but that's the proof. So I'll stick around if you guys have any questions. Thanks for watching.
Thanks. See you, Taylor.
See ya.
Thank you.
Thank you.
You're welcome.
Thank you.